Hello and welcome back to the Basics of Calculus. So this video is going to be the last main instructional video of the introductory section of the course. And today we're going to switch gears a little bit. We've been talking about these ideas of discrete and continuous functions. Just to recap a little bit, we've been talking about, photos and videos, relating that to discrete and continuous math, and really talking about the limit as the center of calculus, and about the rise of function notation, that f of x notation for continuous math. So today what we're going to talk about a little bit is we're going to talk about the two main problems, or the two main questions that are at the heart of the founding of calculus, really at the heart of the ideas of calculus. These are going to be the rate of change problem, so the rate of change problem, and the area under a curve, or more generally, just the area problem. So we're going to talk about each of these in a little bit of detail, and then we're going to kind of conclude by talking about the solutions to each one. So the first problem is the rate of change problem. So for those of you who don't know what a rate of change is, or maybe you don't remember, a little refresher, for if we have a linear function here, say we have this function where f of x equals 2x plus 2, the rate of change is just defined as the amount that f of x, or that y changes, or the change in y for some change in x. So what it's saying is if I change x, or my input, by some amount, it's how much y changes in response. So that would be, so for example, if x equals 1 here, my function value f of 1 is equal to 4. So we have 4. If x equals 2, so f of 2, my function value is going to be 6. If I have f of 3, so let's go 3 over here, I'm going to have 8. And you see where this is going. So what we can see here is that as x increases by 1, so plus 1 in the x, we can see that our y value increases by 2. And the same thing happens when we go from 2 to 3. We increase by 2. So what we would say is that our rate of change of this function, our rate of change, is just 2. Because for an increase in x of 1, we increase by 2 in the y. And so what if, for example, I said I'm going from 1 to 3, you'd see that from 1 to 3, that's an increase in 2 of x, and we get from 4 to 8 in the y, so the y changes by 4, we go from 4 to 8, and from 1 to 3 in the x, y, well, the x increases by 2, so that's a change of 2, and the y increases by 4. That's a change of 4. And so when we say the change in y for some change in x, that's really just a sign of division. So it's going to be like a unit rate. So the amount of change in y for a change in x of 1. So we can divide that to get the unit change, which would be 4 divided by 2, which is still just 2 again, right? We're going to get the same rate of change in this case. And all that we were doing there was just finding that unit rate of change. So the rate of change of this function is going to be 2. And if you notice, if you look back at the function that we have, then 2 actually appears in the function. It actually appears twice, but what I'm more concerned about is that it appears here as the slope of the function. When we write this in general notation, and we'll talk more about this linear equation notation later if you don't recognize it, we write y equals mx plus b. This m here is the slope of the function. And that's actually the reason that this slope is the rate of change. The reason they have the same value is actually for a very intuitive reason. If you think about it, this slope represents how the output is directly related to the input. Of course, there is this extra constant, but this right here, this m, erase that. This m right here tells you how much to increase y for some increase in x. And so that's why the rate of change of a linear function, so rate of change of linear f of x is the slope, is just the slope. So we can always look at a linear function. For example, we could look at y equals 7x. And we could see that the rate of change is just 7. Rate of change is just 7. And that's a really important concept there. But the problem we run into is that while we can do that for a linear function, what happens if we try to do that for, say, a different function, maybe a quadratic function? So a quadratic function is just a function of x squared. So we get that y equals x squared here. Well, let's see the rate of change here. Let's start with x equals 1. So f of 1 equals, well, it's just 1. So we get 1 there. What about f of 2? Well, if we go to 2, we get that 2 squared is really equal to 4. So f of 2 is 4. So you might say, oh, well, I know what it is. I know what the rate of change is. X increased by 1, this increased by 3, so the rate of change must be 3. And in a sense, you're right. That is the rate of change at this point. However, we can check and we can see, is that actually the rate of change of this function overall? Because what if we go from 2 to 3? Well, 3 squared is 9. So f of 3, so I'll write these again. F of 1 was 1. F of 2 is 4. F of 3 is 9. We can see that this one increases by 3, but this time it increases by 5. So we can see that these rate of changes are not equivalent. So this function does not have a constant rate of change. Quadratic f of x does not have a constant rate of change. In fact, it's changing what looks to be linearly, but we could check again, we could make sure. So 4 is 16. So f of 4 is 16. And the change from 9 to 16 is going to be 7. And so yeah, we actually see that the rate of change is changing linearly. So we can see that it goes from 3 to 5 to 7. So not the function, but the rate of change increases by 2 every time. That the rate of change is increasing linearly. So quadratic f of x does not have a constant rate of change. It has a linear rate of change. We won't really talk about that in more detail until we get to another section of the course, but what we can see is that it does not have a constant rate of change. So the question here is, how can we find that linear function that describes the rate of change of this quadratic f of x? Or more generally, how can we find the rate of change, and I'll abbreviate that, how can we find the ROC of any function, not just a linear function? And the answer to that is actually going to be this thing that we'll talk about more later called the derivative. The derivative is the solution to the rate of change problem, to the ROC problem. In fact, the derivative actually describes the function that is the rate of change of any given function. So the derivative is the rate of change. So then, if I asked you, if we go back up to this linear function up here, if I asked you, what's the derivative of this function of f of x equals 2x plus 2? I'll actually go down and write that down here now. If I go down here and I ask, what is the derivative of f of x equals 2x plus 2? Well, you can look at that and you can say, well, the derivative is just the rate of change. And we know the rate of change of a linear function is the slope. So therefore, the derivative of this function is just going to be 2. It's going to be the slope. So the derivative of any linear function is just its slope. The derivative of a linear function is just its slope. And if we look at the quadratic function, we'd see that the derivative of a quadratic is going to be a linear function. And we'll talk about that more later when we get into derivatives. We're going to have a whole section In fact, 2 whole sections on derivatives. And we'll talk about that more later, but all you need to know is that the derivative is the solution to the rate of change problem, and that it's really just the derivative is the rate of change of a function. So from there, now let's talk about the second main problem at the heart of calculus. That's going to be the area under the curve problem, or just more generally, the area problem. So the thing here is that up until the foundation of calculus, up until the founding of calculus, there's really only one way to compute area, and that was if we drew some composite shape. So if we drew some composite shape like this, then we could split it up and say a rectangle, 2 rectangles and 2 triangles. If we want to find the area, it would just be the area of the big rectangle plus the smaller rectangle plus the small triangle plus the bigger triangle. That gives us the total area. We could use composite area. But what if we had an irregular shape? What if the shape was irregular? So say I draw you that shape. How would you find that area? Well, there's no rectangles or triangles or circles you can split this up into. However, you might recognize that maybe we can approximate the area. Maybe we can draw some boxes that we do know how to find the area of, and we can approximate the area. And that's kind of the whole idea behind the solution to what's going to be the area, or the area under the curve problem. That we can kind of split this up into little boxes or little rectangles that are going to give us that area that we want. These little rectangles here, they give us that area. And if we add up all of those rectangles, we add up these rectangles, it approximates the area. So in a more specific sense, we also want to know, what if we have area under a curve, or that is area under a graph? So same concept, except now we're going to graph it. So we have some function, not really going to give a definition to this function, but say it looks like that. And we want to find the area between 2 points. And this may seem like a really weird exercise. You may be wondering why this is important. And it was actually important to Newton for a variety of physical reasons. He was trying to do a lot of math involving the orbits of the moon and the planets, and he ended up needing to find the area under a graph, but it's still related to this idea of just area up here. So he wanted to know, how can I find this area right here? How can I find this area under this graph? And he started thinking about what we had talked about with those irregular shapes. He thought, well, what if I take this area and I split it up into a bunch of rectangles? I can just take these rectangles and add them up, and of course they're not going to be completely accurate. It's just going to be an approximation. But if I add up all of these rectangles, then I can get that area underneath that curve, and that way I can find that area. So the area under a curve was just going to be given by adding these rectangles, adding rectangles under the curve. And you can see actually that the rectangles, we can find their length and width. So the area of each rectangle, of course, is just length times width. We can find their length and width we can find their length, their height, by taking a function value at the rectangle. So it's just going to be f of some number, in this case f of a. And then this one at the end here would be maybe f of b. And these in the middle are going to be adding some distinct interval between them. So this one's going to be f of a plus n, f of a plus 2n, and so on and so forth. So that's going to be the height, and of course the width is just going to be the interval. So it's going to be the area equals f of the point times the interval, which we'll just call n. And so that's how we're going to add up all of these rectangles, by just finding that length and width and adding them all together. And what's really important about that is, if you look, maybe you can start to see this. If we make the rectangle smaller and smaller, we can get a better and better approximation. If you look, what we just drew there is a lot better of an approximation then say we draw the same graph, or maybe this is a little bit different, but we draw this graph and we take just 2 rectangles here. Well, in that case, the 2 rectangles, they're going to really overestimate that area because of this extra bit right here and that extra bit right there. And you'll say maybe they don't include that, but still that really doesn't account for all of this extra bit right here when you compare it to this, which only has very tiny amounts. So an important fact about this is that Newton saw that as rectangles got smaller, and therefore we use more and more rectangles, so as rectangles got smaller and we use more rectangles, the approximation got better. And that approximation is eventually going to lead to the answer that's not just an approximation, but a legitimate answer to the area under the curve problem. So that the solution to that problem is going to be what's called the integral. The integral is going to be the way that we can find the area under the curve. So the area under a curve, the solution is the integral. The integral is the solution to this problem. And I won't tell you really anymore, but it does have something to do with the idea of a limit related to a limit. And in fact, so is the derivative. But they're both related to this idea of the limit, and that's how we're able to get these not just approximations, but actual solutions to these problems. The integral as the solution to the area under the curve problem, and the derivative as that solution to the rate of change problem. The derivative as the solution to the rate of change problem. Sorry about that, by the way. So I think that's all for this video. This is the last instructional video, as I said, of the introductory section. I hope you've learned a lot so far. I hope you have a better understanding for kind of the nature of where calculus comes from, and really the ideas that are beginning to set up calculus in the long term. So I hope you've had a good time so far. Thank you so much. I hope to see you next time.